So in the last video, we were looking at the pendulum and we said it only depends on the length and the acceleration due to gravity. I just want to point out the mass at the end of the pendulum and also the amplitude, how far back you pull it, how many degrees, are inconsequential to the period. They have no impact whatsoever. Let's just show that. Take a moment to do that. So here's the pendulum. I can add a second. And as long as their length is, well, before I add the second, let's go back to 1. And I'm going to pull this back and let it fly. Now watch what happens if I make it way shorter. See how much faster it's oscillating? The period is way shorter. If I make the mass really small, it still takes the same. Let me start over. And you know what? At this point, let me grab the other one. I'm going to put them both at the same length. I'll put them both here. And I'm going to make block 1 huge and block 2 really small. Let me pause the video. Pull them back. They have the same length. They're both on Earth. And they have the exact same period, even though their mass is different. Now let's do this. If I make gravity weaker, or let's do stronger, you see how they're swinging faster now? Alright, and as our last experiment, let's do this. I'm going to put one at maybe 13 degrees and the other at perhaps, 6. And I want to see, does one take longer than the other? They have different amplitudes, right? One is pulled farther back. It has a larger maximum displacement. Let's see. Look at that. They are oscillating right in step, always reaching the edge at the same moment. So that's pretty cool. Yeah. Length and G, those are the only things that matter. On Earth, of course, at the surface of Earth, G is 9.81 meters per second squared. The last thing I just wanted to point out, compare this to this. They are reciprocals. Therefore, T and frequency must be reciprocals of each other, which is where we get this equation. Okay. Now, when we were first starting out, we said that, okay, well, when you oscillate, you can oscillate like this, where you never lose energy, or we could add friction. And eventually the systems, they kind of slow down and eventually stop. This type of system where there's friction is not so simple. But what if there is no friction? What if we have kind of the simplest, purest, free-swinging example? We call that simple harmonic motion. If you want to think about it physically, simple means free-swinging. No friction. The person is not coming along and bumping into the pendulum. It's just swinging on its own, freely. But mathematically, here's what we can say. Okay? There are two conditions, mathematically, that have to be true for the oscillation to be simple harmonic motion. First, the net force, that restoring force, must be opposite the displacement from equilibrium. That's the first condition. 2. What does that mean, by the way? All that means is, here's the pendulum. Let me make that straight down. Here's the pendulum. If you pull it to the left, if you displace it to the left, the restoring force is opposite in the other direction, back toward the center. If you displace it to the right, the restoring force is in the opposite direction, back toward the center. The second condition is the net force must be proportional to the displacement from equilibrium. Look at this. Look at how specific we're being. We say every time we say the displacement from equilibrium. That's part of the answer. If this were on a test as a short answer, you would have to say from equilibrium. That's included as the answer, as part of the answer. So what does that mean? Well, if you go farther out, that's a bigger displacement. And a bigger displacement means you're going to get pulled back toward the middle with more force. And if you're not so far, that's a very small displacement. Here we go, not so far away. That's a very small displacement. So there is a weaker force. Okay. The force is directly proportional to the displacement from equilibrium. We can summarize both of these in a wonderful equation. And the equation says the net force has to be negative a constant times x, the displacement from equilibrium. Because this shows a direct proportionality, that's condition 2, and it also shows the negative sign, which is condition 1, that they're in opposite directions. So, is it true? Does the spring force actually satisfy this equation? Well, let's look and see. Let's imagine that the spring is stretched out like this, and it's on a frictionless table. Okay, here's the center position, or the equilibrium as we say. The displacement is to the right. And because of that, the spring is pulling the block in to the left, F spring. So bam, already we know we've satisfied the negative sign because they point in opposite directions. Displacement and force are in opposite directions. So we're good there. Well, what other forces will the block feel? There's a normal force, and there's a gravity force. But when we add the forces to get the net, what do we find? Fn cancels mg, and the spring force is simply equal to negative kx, where k is the spring constant. And look at this. That is beautiful, because this clearly satisfies that form. The general requirement, bam, we've got that taken care of for this case of the spring. Now, I'm not going to prove the case of the pendulum because it is a little bit more involved. It takes quite a bit more work. But let's just show what that force is. Here's the pendulum off to the side, and it stops briefly when it gets to the edge. When it, here it turns around, it stops, and then it swings back in toward the middle. So what are the forces that act? Well, there's tension acting along the string, force of tension, and there's gravity pulling the pendulum back down. Now we have to be careful this time. We're going to use tilted axes, not the normal xy axes. So the tilted y-axis will be along the string, and the tilted x-axis will be perpendicular to the string. There's the x-axis, there's the y. So force of tension, that's on the y-axis. I don't need components. Force of gravity, though, that's not on the y-axis. So let me draw a tilted x component and a tilted y component. We can see that the y component will cancel the tension force. So the net force will just be that tilted x component. You see where that thing is pointing? Let's draw the pendulum when it's back down in the middle. This force points right back toward the center. That's the restoring force. And with some work, it is possible to show that that restoring force is equal to negative a constant, I'll just call the constant c for now, times theta, the displacement from equilibrium. It takes some work, but that is possible to show. These two conditions and the equation we wrote down are really, really important. If there is short answer on the next test, this is almost certain to show up. Negative a constant times the displacement. But of course, net force is equal to mass times acceleration. And while, the constant is here, but the mass, that doesn't change either. So if we divide both sides by mass, we can just build that mass into whatever the constant is. Just modify the value of the constant, and mass is basically going to disappear because this is all just a constant. So the equation, when we write it with acceleration, is a is negative a constant times displacement.